Thanks for coming out tonight, everyone. I kind of want you to adopt a mindset for this presentation that is sort of different from our ordinary kind of like perception of the place where we live. Like, we kind of think of the ground surface below us as just sort of like this area that we can choose to change, kind of like how we would like to change it. And if we want to plant something there, we will clear some space and try to plant it. But I want you to try and take a different perspective on things and think about the state of Ohio as one big organism. And it's basically connected from its bedrock through its native vegetation onto up through the organisms that utilize that native vegetation for their food and shelter as one integrated whole. So when you encounter a bare patch of ground in this integrated whole, think to yourself, what does this want to be? And to answer that question, we should go back in time. Okay, so I'm going to talk to you about the evolution, or kind of like the growth of Ohio from the time of its inception. So I guess like this is back when Ohio was a baby. All right, so like here you can, so first of all of the bedrock, which is the topmost rock underneath the soil, all of the bedrock in Ohio is sedimentary in nature. So this bedrock started getting deposited in Ohio, let's see here, it was 450 to 290 million years ago. That's the period of time when all the bedrock was deposited. And at the start of, and during that time, at least at the start of it, yeah, so like, all right, this is Ohio when, like, at the time of its first inception. And so it was like 20 degrees below the equator, and it was also underwater. Here's a close-up of it. And during the time of Ohio's bedrock deposition, it's basically going to migrate northward to about 5 degrees north of the equator, but all of the time it's going to be in the tropical latitudes, which is kind of like strange for us to think about. But like this same like, you know, like shelf of land that we're sitting on, this is where it was during that time. All right, so yeah, tropical times. All right, so the first 3 large periods of bedrock deposition in Ohio happened when Ohio basically occupied an environment that's similar to what's called, what's that? the Bahama Banks. So like, there are environments right now on planet Earth that mimic like the situation in Ohio back in its early inception, and those are the Bahama Banks. What it is just a shallow tropical sea, and in this shallow tropical sea, you have limestone being deposited. And like, for those of you who just really like to know the details of like what's going on with this kind of thing, I have here written the chemical reaction by which limestone gets deposited. So essentially, you have, like, calcium is a common mineral in the Earth's crust, and underlying, like, basically like underneath this shallow sea, you've got lots of mineral matter that has calcium bound to it. Calcium can get released into the water column through a process called hydrolysis, and at that point you have calcium sort of loosely associated with with basically like part of the original water molecule that's negatively charged. What happens next is carbonic acid falls into the sea from rainwater and dissociates so that the carbonate, the CO3, precipitates, which forms a solid with the calcium, and that's how you get calcium carbonate being deposited in that, on that shelf. Okay, so anyway, this is what's happening in Ohio for the first half of its depositionary cycle. What's really interesting is that the bedrock beneath our feet, when we're talking about limestone, is actually the shells and bodily fragments of marine organisms. So this, and if you take a close look at it, you can see those shells. And the reason why, I puzzled over this for a while. I'm like, I don't get it. If the conditions in this tropical sea were conducive to limestone formation, wouldn't it be happening anyway? Why do we need these, what do the mollusks have to do with it? And actually, it does happen spontaneously. So if you were wondering that, the answer is yes, it does happen spontaneously, but the mollusks have enzymes that speed up the reaction. So, and another thing that just drove me nuts when I was researching this was you'd encounter statements like, when the sea was clear, the mollusks would be accumulating a great amount of calcium carbonate, but then when the sea was muddy, that would cease. And I would be like, why? And it's simply because they moved out. They don't want to be in murky water, so they went somewhere else. This doesn't mean that limestone precipitation stopped happening. It just means that it slowed down greatly. So this is why, if you look at sedimentary bedrock from these early times, you will have layers of limestone, and then you'll have a layer of shale. And sometimes it's limey shale, but oftentimes it's not. And it's simply because mud was flowing into the sea at that time, and the mollusks just packed up and moved out elsewhere for a while, or died, but they didn't all die. All right, so anyway, that was the sedimentary depositional environment for the first half of Ohio's kind of bedrock history. It was that shallow Caribbean Sea. And what happens next is the sea retreats a bit, and sediment starts to accumulate to a greater extent, and Ohio starts to emerge from underwater. And it forms no longer an environment like the Bahama Banks, but rather it forms an environment like present-day Louisiana. So this is what's going on during the second half of Ohio's sedimentary cycles. What you have are mountains that are rising essentially where the Appalachians are right now, and a tremendous amount of sand, silt, and clay is getting eroded from those mountains, and it's making its way into Ohio, into that shallow water, and it's building river deltas. Oh, a river delta? Yeah, a river delta is basically is just when land starts to extend outward into a gulf or a body of water because sediment that's being carried by a river is being set down in that place. That's what it is. Yeah. All right, so anyway, so this is the sedimentary environment until the seas retreat a bit more, the delta becomes a little more well established, and all of a sudden Ohio's not underwater anymore. It's dry land, and that ceases the time period of sedimentary deposition in our state. Okay, so if you look at a bedrock map of Ohio, you're going to see this kind of pattern of north-south stripes, and you're going to be I don't get it. I thought everything was being deposited one layer on top of another. But look down in the corner here, and you'll see that the layers were getting deposited one on top of another, but the western half of the state is actually elevated slightly compared to the eastern half of the state. So this means that the depth of sediment deposition was greater in the eastern half of the state, and also it means that once the water retreated and Ohio was dry land and erosion started, the erosion was most focused on this western ridge, which was called the Cincinnati Arch. So like, this is actually pretty interesting. Like this yellow layer right here, it actually originally connected to the one over here. And definitely, and I think, yeah, so that's definitely the case. These were connected, and when like whatever, the ocean, the seawater retreated, it basically just got eroded most focally on that ridge. All right, so anyway, oh, and this also, what this means, like this pattern of erosion and deposition, it means that the oldest rock is going to be on the ridge that was eroded, the Cincinnati Arch, and the youngest rock is going to be this stuff over here in the eastern corner of the state. That's like the, so like these are like the deltaic, like when it was like Louisiana over here, and then over in the western part of the state, that's back when it was like, you know, the Bahama Banks. All right. All right, so once Ohio became dry land, all of that bedrock that had been deposited started to undergo like basically the forces of soil formation. And these like so you've got solid bedrock, and it needs to get turned into like loose soil. And the main means by which that happens are like physical processes like freeze thaw, where it expands and contracts and just gradually crumbles. And probably the main way that it happens is just through like the infiltration of water, and on a molecular level, water performs that hydrolysis reaction that I told you about earlier, that was happening when it kind of like separated calcium from the underlying minerals. So anyway, the soil in Ohio is like, or whatever, the bedrock is weathering, it's forming soil, and what's happening is, all right, now hold on a second here. Oh yeah, what you need to understand, and this is going to become very important later in the story of Ohio, is that the limestone that was deposited is able to make acid disappear. And acid is constantly getting rained down upon us, literally, because carbonic acid forms through water reacting with carbon dioxide. And when the acidic part of the carbonic acid reacts with the half of the limestone mineral, it forms carbon dioxide and water. So the acidity goes away. But what this also means is all of that limestone bedrock that was deposited is gradually disappearing, it's getting dissolved, it's leaching downward, and it's turning into CO2 and H2O. So, when you started out, you had like limestone bedrock that was like a pH of like 8, which means like there's not only zero acidity, but there's negative acidity. What starts to happen is like from the surface downward, it starts to get more and more acidic because the limestone is retreating to a greater and greater depth. So like, even though Ohio is underlain by all of this limestone bedrock, our soils should all be really acidic, right? I mean, this has been weathering, like this limestone, the last time it was deposited was like what did I say, like 250 million years ago. So that's plenty of time for this to happen. But what's really, oh, and this is just like, whatever, a representation of the pH scale here, so you can like kind of wrap your brain around it. Lemon juice is a pH of 2. So anyway, all right, so what's up? Well, I'm gonna get to that. Yeah. All right. So, all right. But anyway, like what we would expect is we would expect that, like, yeah, with all of this rainfall and all of the retreat of the limestone and the, you know, the neutralization of the acid, that all of our soils would be quite acidic. The only way for us to avoid that scenario essentially would be for us to get submerged again under, like, you know, ocean, back in the sea. It didn't happen. Something else happened. We got basically, like, we got buried under a mile of ice. And this happened, I mean, fairly recently in geologic times. Like 780,000 years ago is when the first like continental ice sheet came through, and then there were like 2 subsequent ones. The last one left only like 10 to 14,000 years ago. What's crazy is, like, you can actually wrap your head around that number. I mean, we'll all probably live to be 100, and like 10 times our lifetime is 1,000. And I'm telling you that the last glacier, like that, retreated 10,000 years ago. Like, you can actually conceptualize that number. So it wasn't that long ago. But all right, so what's the big deal, and how does this like influence the story of Ohio, these glaciers coming through? Well, first of all, they didn't cover the entire state. They only made it down 2/3 of the way. But I'm going to show you in a second what they did to our soils. All right, look at, all right, this is a, no. The glaciers are good. I'll tell you what, think about it. The glaciers, our soils, I got 2 phrases for you that you can think about. Our soils are a gift from the glaciers, and glaciers are soil factories. Okay, because, all right. So, all right, so this is like a glacier in cross section. And what's happening is, like, if you can think back to that soil profile that I showed you a little bit ago, where the surface of the soil was very acidic, and like you only got to like the neutral part just above the limestone bedrock. What the glacier does is it pulverizes the bedrock. That then gets like shifted upward in the body of the ice, and it mixes everything up. Basically what happened is the glaciers set back the clock. They turned it back to time 0, where the soil was like circumneutral, because they mixed up the underlying bedrock with the overlying acidic soil. So it's like we got a fresh start. This means that our soils were, like, once when the glaciers pulled back, they were once again like pH 7 only 10,000 years ago. And then, of course, like, the rainfall happens. You have like the dissolution of those like surficial carbonates and whatnot, and you have the moving downward of the process. But anyway, we got a new start with that. Okay, so the glaciers. Oh, but here, I'm going to go back for a second. However, we have kind of. But look at the southeastern third of the state. They didn't get that start over time. Like, they didn't get the clock turned back on their like pH weathering. They've been essentially weathering and leaching nonstop for 290 million years. They've got to be worn out. All right, so what else did the glaciers do? Obviously, they affected the pH of our soils, but they also affected the texture of our soils. Up in northwestern Ohio, as the glacier was retreating, and it was like a really massive ice sheet up in this space, because like the further north you go, the more it weighed. It blocked the outflow for like the natural waterway. It excavated what is now the Lake Erie Basin, and since the water had no way to go, it accumulated to a great depth. And in this standing water, sediment was released by the melting glacier. It takes a longer time for fine sediment to settle than it does coarse sediment. So this means that what's left behind after the lake retreats is what was on top. And what was on top was superfine clay particles. So that means that northwestern Ohio has a concentration of what's called aquic soils. And these are soils that are superfine textured, and they really retain a lot of water. And they became the basis for a giant plant community, really an entire ecosystem known as the Great Black Swamp that extended 15,000 square miles. And this is like a really special thing about Ohio, is that if you look at like a map of soil water regimes for the entire North America, aquic soils are generally only found along the coastlines and in river basins. But Ohio is special because right here in the Midwest, we have this huge area of aquic soils where if it were left to its own devices, it would turn into a giant swamp once again. And, you know, I think that we should kind of think forgivingly of the people who drained this space, because we're all human beings. We all kind of like share in the struggle, and those mistakes are something that, well, I wouldn't even call them mistakes necessarily, but the point is that our story is an evolving one, and just because it was drained doesn't mean that we can't restore some of this into some really outstanding wetlands habitat, and that's actually happening. So I know that like the city of Toledo created a very large wetlands metro park recently, and hey, this land is just waiting to be the Great Black Swamp once again. Oh yeah, so this is just a little more like information about like what those lacustrine, they're called lacustrine deposits, like that really fine, the really fine clay deposits that happen in northwestern Ohio. They form these layers, and that's simply because, like I was telling you, that like it's because of like the fine sediment falling out of suspension more slowly than the coarse sediment. Okay, so yeah, this is just like a little bit of like insight into the soil parent materials, like from which our current soils formed. All right, but southeastern Ohio, the part that was never glaciated, the part that was basically like getting heavy deltaic deposits. What is the parent material for there? What kind of deposits were their soils being formed from? And the answer is sandstone largely, also shale, also siltstone. But here's an example of sandstone bedrock. It's very resistant to weathering. This is in Clear Creek Metro Park, and this is an example of like weathered sandstone. And this is just a basically to show you like what a soil, like as like the weathering of the parent material happens, like what the resulting soil profile looks like. And I just wanted to like give you a picture of like what Ohio's pH distribution looks like because of the action of the glaciers and the previous oceanic history. It's pretty cool that our state has this kind of assortment of pH in its soil. Another reason why the soils in southeastern Ohio have lower pH though than the rest of the state, it's not just because of the dissolution of the carbonates. It's also because some of the clay in southeastern Ohio is actually structurally different than the clay in the rest of the state. Clay has a negative charge due to the fact that when it forms, the molecules in the clay layers that have a negative charge, the oxygens and the OHs, they outnumber the positive charged ions. So like that might be like, well, who cares? But actually it's really fortuitous for like the growth of plants, because since clay has a negative charge, it's able to attract nutrient elements in the soil solution, and it basically holds them there for the plant roots to obtain. But the other thing that it does is, since it's negative charge, it can pull acid out of solution, and it can prevent soils from acidifying after the limestone has dissolved. And in southeastern Ohio, what happens is when the pH drops below a certain level, you have the dissolution of aluminum, and it'll block up the layers between the clay, making it less able to pull acidity out of solution. So, like, I've basically just told you, like, probably more detail than you'd want overview of like how we got to this point. You know, we had the shallow sea, we had the deltaic deposition, we had the glaciers, we had like aluminum gunking up the layers of our clay and making it less able to pull acidity out of solution. But like, what does it all mean to our native plant communities that utilize those soils? Check this out. If you look, this is the map of Ohio's glacial deposits. This is a map of Ohio's pre-settlement plant communities. And this is another map of basically a prediction of what the climax plant communities would be in Ohio. And the correspondence is undeniable. But I don't know, maybe it's just a quirk of mine. I kind of like to find out for myself, and I kind of like to, well, whatever. Information is more meaningful when you experience it with all your senses. So why not head out to the field, seek out the plant communities, and find out, are the soil properties really corresponding to the different plant communities? All right, let's go. So, the first place that we're going to go is a place that is known to have a lot of beech maple. Here, hold on a second. Sorry, let me just go back for a second. Oh yeah. All right. So like one of the main climax communities is the beech maple forest. All right. And the beech maple forest seems to correspond roughly to this boundary of glaciation. So the first stop is finding a beech maple forest and finding out what does the soil look like under the beech maple forest. So where I went was, it's called Emily Trefagin Park. It's in Delaware County. It's part of the Delaware Parks and Preserves. Anyway, here's a, like, I don't know if you can, I don't know, oh shoot, I don't know if you can see this, like, it looks kind of like spotty, but like, this is just like a diagram of the soil bodies in this space, and the one that I was sampling was called the Blount soil, and it's on slightly elevated, and it formed in glaciated regions from till. All right, so this is what I found. This is what the soil probe reveals in terms of the soil appearance, the morphology, from a 0 to 12-inch depth. The pH was 5.5 in the top 4 inches. The texture was silt loam. Below that, the pH was 5, and below that, the pH was 5.1. So this soil all formed in like limestone till. And this is just showing what we already knew, is that the acidity is encroaching downward, and as that limestone is getting dissolved and neutralizing the acid to a greater and greater depth. But meanwhile, this is what the forest looks like on top of it. These are our American beech trees, and here's a shrub layer that was almost entirely, spice bush. All right, so, wait, what happened there? Okay, oh yeah, here we go. So like, this is just a description of the plants that were growing there. Over 80%, in my observation and estimation, American beech and sugar maple. Lesser amounts of like some other trees, like you might not be familiar with, but like eastern hop hornbeam was the most abundant tree other than those two heavy hitters, American beech and sugar maple. And then there were lesser amounts of hickories and northern red oak. Lots of spice bush. The herbaceous layer, here's a picture of the herbaceous layer. It had like, I don't know, just like a variety of like herbaceous plants. But some of them have kind of like whimsical names, like enchanter's nightshade and clustered black snake root, jewelweed, jumpseed. All right, so the descriptive community name that I would give to this plant assemblage is the beech maple forest community, definitely, because of the predominance of beech and sugar maple. And this is just kind of an artistic impressions of the beech maple forest, because I don't think that looking at the numbers really gives you a feel for what it's like to be there. And you have, there's a word for this, but like American beech gets this beautiful kind of like almost like liquid appearance to its bark. What now?
Sexy, I think it's
Yeah, there you go.
No, not beech.
Hey, that's perfect. It's like it was meant to be. All right, so then like, no, I mean, hey, Don, you can like have your opinion, but I disagree. I think beech is pretty sweet. So, and then like, all right, so here's the formation of a vernal pool over here where a beech toppled over. So like, you know, even in death, there is this really wonderful place for new life to happen. And that, you know, that's really the story of the forest in a nutshell. And here are some other, like, here's jewelweed, jumpseed, lopseed. These are just like native herbs. All right, so that's the beech maple forest. That's the climax community for like a big part of the state. And now we know what's going on in the soil underneath the beech maple forest. We know what it likes. You know, it does, like, when I saw the boundary of the Wisconsin glaciation and I saw where the beech maple forest grew, I was like, these trees like limestone. These trees like circumneutral pH. But you know what? They don't. Beech doesn't like that. And beech, it actually has its, like, you rarely find beech growing in great abundance with soils that exceed pH of 6. You rarely find it growing on limestone soils. So I was like, how can that possibly be? And this is how it can be. It's because of the leaching of the carbonates. That's how it happens. So why are beech and maple growing there? Probably because they like the moisture regime. They really like the fact that these soils are a certain texture, that they're retaining water just in the amounts that they like. And it's on those low swells and slightly elevated flat areas that were created in such abundance by the glacial ice sheet. All right, so anyway, moving on to the next point of investigation. All right, so what we're going to look at now is, all right, so we just looked at like the top surface of an elevated area in the glaciated region. Now we're going to look at the side slopes, and we're going to look at the bottom of that elevated area, what's called the toe slope, the depositional area. And we're going to see, are the plants different? Are beech and sugar maple still growing in those spaces? Or something else growing there? And is the soil different? All right. Well, anyway, we'll look. Yeah. So, yeah. All right. Where did I go? Where did I go to find it? I went to Battelle Darby Metro Park in Franklin County, and this is like. So this is a block diagram of what the soil area was that I was going to be sampling, and I was focusing on the slope of a soil called the Miamian, and I was focusing on this the toe slope or depositional area, and the soil was called I can't read that, but that's not important. The point is that the point is it was a depositional area. So we're going to see if it's any different. All right, here we go. All right. So the position number 2, back slope and toe slope in the glaciated region. The parent material in bedrock are glacial till and alluvium that's deposited by the river down there at the bottom. And again, it's limestone bedrock. We had limestone bedrock before. What did it do for us? We had acidic pH in the surface soil. Is it going to be any different this time? Check it out. It is 0 to 5 inches. This is on the back slope. pH of 6.85, texture silt loam. 5 to 12 inches, boom, we're back up above neutral. And we also get more fine textured. On the toe slope, the depositional area, right at the surface, you're already above a pH of 7. And as you go to greater depth, you still are. So what's going on here? Like, these are like the same deposits, same parent material that we had for the beech maple forest, but the pH is all different. The reason why it's different is because on the slope, the soil has been eroded and it's exposed the underlying deep soil that has those the carbonate bedrocks, which are still fresh and neutralizing the acid in their immediate vicinity. Okay, so what? Like, what does it mean for the plants? Well, it actually has a very pronounced effect on the plants. Hold on a second here. Let me go back. Yeah, this is what the forest looks like here on the back slope of the Battelle Darby Metro Park. I don't see big stems of beech. I don't see big stems of sugar maple. What I see is, first of all, a lot more growth that is extending between the shrub layer and the canopy layer. It's a much denser growth of vegetation. And what about the species that we find? All right. Well, so I kind of combined the back slope and the toe slope. We've got Ohio buckeye, blue ash, eastern redbud, chinkapin oak, eastern hop hornbeam, northern red oak, American hornbeam, bitternut hickory. Look at all these trees. We've got a real variety here, and shrub composition. It's spice bush and something called black haw viburnum. It's a berry producing shrub. Birds love it. Pollinators love it. And then in the herbaceous layer, wow, look at how thriving the herbaceous layer is. Much more dense. And the thing is, this is the herbaceous layer down next to the river. And this is something that's really kind of characteristic of floodplains. They have like a very dense, vigorous herbaceous layer. All right, so what are we going to call this ecosystem? It's clearly not the beech maple ecosystem. Why don't we call it the mesic circumneutral mixed deciduous forest community? And you know what? As an abbreviation, why don't we just call it the sweet soil hardwoods? It's kind of like a nice, accessible way to think about alkaline versus acidic soils, sweet soils versus sour soils. All right, and here we are, impressions of the circumneutral forest. So we have redbud, Ohio buckeye. Did you know that our beloved buckeyes, they like the circumneutral soil? And then we have a few others that fall into that same category, chinkapin oak, and then just some, I don't know, very expressive herbs. All right, so now.
David, you're a
Gotcha. All right. So moving on to, moving on to our final sampling area. We're going to a ridgetop in an ridgetop in an unglaciated region. All right, so we're beyond the glacial boundaries, and now we're in a parent material that is sandstone, and the soil's been forming for like probably 250 million years. Well, all right, there was like eroded sediment, and then until it got exposed, but still, it's been forming for a really long time. And this is in Clear Creek Metro Park. I was sampling up on the ridge tops, the Lily series. All right, here we go. All right, this is what the soil looked like: 0 to 1 inch, a pH of 3.5. Moving down, it doesn't even break 5. This is what the forest looked like. We've got a lot of stems of what's called chestnut oak, and then in the understory you have a dense growth of a plant called smilax. And all right, so this is what the shrub layer looked like. This is what the herbaceous layer looked like. It's not really herbaceous. What you see are just many seedlings of chestnut oak. All right, and what are we going to call this community? We're going to call it the dry acidic mixed deciduous forest community. And why don't we experience it? Yeah, but down there was other stuff growing there too. All right, so here we are, impressions of the dry acidic forest, and we have blueberries growing here. We have, like I said, the chestnut oak and other species that just love that acidic soil. Here's just an overall comparison side by side of what the soils and what the forest communities look like. And I don't think we need to like delve into this again because we've just kind of gone over it ad nauseum. All right, but like, why do the plants care about the soil properties underneath their roots? Largely, they're caring about it because of nutrient availability and because of moisture availability. At a pH of 5.5 to 7, you have the maximum amount of nutrient availability. This could explain why the vegetation was so vigorous in the circumneutral soil. At a lower pH, at higher pH than that, you have limitations on micronutrients, and at lower pH, you have excessive aluminum. But there are plants that like that too, that can deal with it, like the blueberries. All right, so to tie it all back together, what I've kind of like been plotting through, and perhaps you've had an experience of geologic time by listening to me talk for this long. The point is that our plant communities are indeed an expression of the underlying bedrock and an expression of the underlying soil. It's an integrated unit. It's like one big organism, and let's help it thrive. All right, that's all.